Okay, here we go. So, a little bit more about line integrals. A couple of last things I want to say that I think are useful points. So, first thing I want to introduce the idea of something called a coordinate line integral. It's really not that sophisticated of an idea the way we're going to see them here anyway, and that is to just recognize that on our regular formula for what dx is, right, x prime dt, old news, I can recopy x prime, writing it out in coordinates. Right, that's again old news. That's what is that? Chapter 2, right? Nothing surprising there. We've never written it like that before, but we could. Why not? Let's go ahead and do it. Okay. Then here's another thing, a completely unimpressive point, and that is I can distribute the dt. Right? That seems like a weird thing to do, but I mean, surely, what would be wrong with that? And then I can point out, hey, this thing right here, x prime scalar x, that is, scalar x prime dt. I mean, since single variable calculus days, we've been calling that dx. Right? And then likewise for y prime dt, z prime dt. So what we have here is, as a result of just writing everything out in coordinates, we have a coordinate differential representation of our position differential dx. Now, it's just notation. Nothing here should be upsetting or disturbing. Okay, now, having said that, though, here's where it gets a little weird. Vector line integral. Done a bunch of things with vector line integrals. We think of vector line integrals kind of physically, right? The dx represents displacements. That means something geometrically. The integrand, capital F here, right? The vector field F, that represents either forces or fluid flows, something like that. This is all relatable. But if I were to take that vector field and write it in coordinates, and by the way, I think this is a little weird, but it's extremely standard. For whatever reason, it doesn't matter, but it's very typical to write the coordinates as P, Q, and R. Anyway, it's a standard, whatever. Don't look for meaning there. It's just an arbitrary choice. And then if I were to take my new formula for the dx vector, writing it in coordinates, now I've got here a dot product that I can crank out in coordinates. And again, now as a bit of algebra, that's not surprising. This is how you do dot products. You multiply and add. It's a good old-fashioned dot product. But the punchline is, now I have a new way to write a vector line integral. And we can, in fact, think of individually, like I can think of this by itself as a thing. Right? Integral over a curve of p times dx. P is a scalar valued function. Dx is, well, it sure looks like and is basically interpreted as the same dx that we saw back in, single variable calculus. So this is a kind of a strange thing if you really think about it. We're doing an integral over a curve where differentials we think of as being either lengths or displacements, but we've never thought of a differential on a curve being just dx. Just, don't worry about how y and z are changing. Don't worry about the length. Just look only at how the x-coordinate by itself is changing on that little piece of curve. Kind of a weird thing to end up looking at. Likewise, we can talk about the integral q dy separately. We can talk about the integral r dz separately. So these are what we call coordinate line, is what I'm calling, and I believe the book does too, coordinate line integrals. So, yeah.
So are these three different integrals?
But you can write it in sort of either way you like. You can think of this as one large integral that represents this, or you can think of it separately as a sum of three separate integrals. Right? Now, where it gets weird is, okay, well, what does this mean by itself? If I look at integral p dx on a curve, physically, geometric, what is the intuition? How should I think about that thing? And I don't have a very good answer for you, frankly. This thing right here, I have a great answer. If your vector field is force, this is work. right? If the vector field represents the velocity of a fluid, then this is something like its circulation. If it's a closed curve, otherwise we have this point of view. It's how much the fluid is flowing along the curve, and it's semantically weird, but it's nevertheless something we have a physical intuition for. But this by itself, kind of opaque. Right. So let's consider pros and cons then, comparing this notation versus this notation. This notation here is large and clunky, and it is kind of devoid of intuition. Where is the win? Why is this a good thing? Why are we talking about this? Right? It doesn't have any redeeming features that we've seen here at this point, right? And side note, for the purposes of doing Math 219, that's kind of the story. I don't encourage using this notation. In the context of Math 219, it's not really particularly to your advantage to use this notation. So why am I wasting our time on this? And there's two reasons. The first one is what I'm going to call a cultural reason. In Chapter 8, you'll see some discussion. By the way, Chapter 8 is not part of this course. You're not responsible for it. And also, side note, it's a very different feel from Chapters 1 through 7 that we're spending time on in this course. Chapter 8 is very weird. It's very mathy. Significant bump up in the sort of mathy proofiness, abstractness compared to chapters 1 through 7, which are already a little higher cut than we're intending to do in Math 219. So, but if you kind of want to see what I'm talking about, in chapter 8, they will talk about these things called differential forms. And differential forms are ultimately very natural. Now, they're super sophisticated and abstract, but in fact, ultimately very natural and also very powerful. There are things that you can't prove without differential forms. Things that are really important, really insightful, unifying theorems that are otherwise seemingly separate and disconnected from each other. Powerful connections between calculus and other fields that you never in a million years think were connected to each other. It all comes out of differential forms. So differential forms are a really big deal. I'm a fan, right? But it's all beyond Math 219, and so it's not it's not stuff that you really need to know. But I do want you to know that this notation is related to some very cool stuff. And as a result of that, now this gets into the second reason that I think you need to know this notation. This notation, because of all the wonderful things about differential forms, this notation's out there. It's very much in common use. There are some books that I've seen, engineering books in particular, where they prefer this notation. And again, they have their reasons, right? There's really good reasons why they would prefer this notation. So the main reason I'm showing you this is I want you to be aware of it. Again, culturally, there's good reasons for it, and I want you to know what to do when you encounter it in the wild, right? Outside of this course, you're going to. And when you see this, you need to know what to do with it. Side note, what do you do with it? Well, just recognize when you see this notation that the P, the Q, and the R are just a fancy way of telling you what your vector field is. Right? And the dx, the dy, and the dz, that's just telling you that you're doing a vector line integral of that vector field, PQR. Right? So, roughly speaking, when you see this, I want you to think this. Does that all make sense? Alright. Okay. So, coordinate line integrals. Next, symmetry theorems. Again, y'all know I'm a big fan of symmetry theorems. Excuse me. And good news. For scalar line integrals, we have a symmetry theorem. It's exactly what you would think it is. Notice, again, I have deliberately laid it out on the page exactly like I laid it out on the page for double integrals and for triple integrals. And it's extremely powerful, and I've scored 1,000,000 times using this theorem. It's awesome. So the function's got to be odd. The domain In this case, a curve, of course, has to be symmetric. It's got to both have to be true. It's got to be over the same line for each of the, oh man, my stylus. It's got to be over the same line for both of these requirements. And it's exactly what you think. It works exactly like you would expect. So, good news. Go ahead. Here's the catch. This is importantly, specifically only for scalar line integrals. I cannot emphasize this enough. It's only for scalar line integrals. And this is another reason that I think it's very important to make a distinction between scalar line integrals and vector line integrals. They are different critters. And in particular, if you were to try to apply this to vector line integrals, it does not work. There is no odd symmetry theorem for vector line integrals. And it's not that it just hadn't been proved or hadn't been written down. It's that it's false. It's not true. You can't because it's wrong. So beware. Now you could argue this is another landmine about symmetry, right? If you get a little too symmetry happy, again, don't get me wrong, I'm symmetry happy, right? But if you're too symmetry happy, and if you try to apply odd symmetry to a vector line integral, then everything you've written down is wrong nonsense and irrelevant to any sort of valid solution. And it's just there's nothing there that could that as a grader we can rationalize giving points for. So please be careful with this. Please do not try to use odd symmetry for vector line integrals. For a quick intuition of why that is, here is a curve. My attempt anyway at drawing a curve that's symmetric over a line. And you can see that I could chop this up into little pieces, and I could talk about this piece and that piece being reflections of each other. And these have the same ds. Sure, they're the same size. But don't forget, when you're talking about a vector line integral, let's see here, color choices. If you're talking about a vector line integral, right? There's also this, let me switch to pencil mode. There's also this dx thing. Dx, of course, is TDS. And if you look specifically at the t, notice that the t's for these two chunks that have the same ds, that are perfect reflections of each other, the t's are just unrelated. They're not equal to each other. They're not opposite of each other. They're just different. Unrelated. Well, that's a bit of an overstatement. But they're not equal, they're not opposite, and so there's no way to make an odd symmetry theorem work. Everybody with me? Okay. Now what you can do, and this is fine, is if you find yourself looking at a vector line integral, what you could do is rewrite it as a scalar line integral, compute this integrand, f dot t, right? And with the t factored in, if this is odd, then will you in fact have then an application of the odd symmetry theorem for a scalar line integral? At this point, having done the f dot t, it is truly a scalar line integral after that point. And then, yeah, sure, for that, go ahead. You're basically just using this theorem, and that is fine. Okay. All right. Okay, pausing for questions. Everybody okay? Okay, new topic. Exciting new topic. We're gonna. This is going to be our first glimpse into a really beautiful set of ideas. The stuff that we're about to get into is why I really enjoy teaching multivariable calculus. It's really beautiful ideas. There's a lot to say. I shouldn't get too far ahead of myself, but anyway, the downside is there are a lot of ideas. They are new. They're different. They're, I'm going to say, basically unfamiliar. And so there's going to be a lot to absorb here. And so make sure to give yourself the necessary time to digest all these very new ideas. A complete understanding of which will require a lot of digesting. So anyway, let's dive in. We're going to start with something called Green's theorem. And here's the first idea that we have to talk about in order to make sense out of Green's theorem. There's going to be several sort of disjoint ideas that we have to talk about separately, and that'll all come together in a few pages, probably by the end of today, fingers crossed. First thing I want to talk about is the idea of boundary. Now, we've talked previously about curves. At this point, if you're talking about vector line integrals, which we will be in just a minute, if you're talking about vector line integrals, your domain is not just a curve. Your domain is an oriented curve, and the oriented part is very important to the understanding of what a vector line integral is. So, all right, well, if you think about it, if you ask what the boundary of a two-dimensional region is, well, the boundary is going to be a curve. Oh, wait a minute, we need an orientation, right? We're in the realm of talking about vector line integrals. Those take place on oriented curves. It is no longer acceptable to think of a boundary as merely a curve. I need an orientation. Which of the two possible orientations do I mean when I say the word boundary? Rhetorical question. There is an answer to this question. It is a convention. It's arbitrary. Planet Earth could have decided 150 years ago to make the opposite choice. Doesn't matter in that sense, but 100 and some odd years ago, the decision was made, and we have to get on board with that decision. It's kind of like, I don't know if y'all have, how much physics y'all know, but electrons and protons, right, have charges. Protons are positive, electrons are negative. Arbitrary choice. They could have gone the other way with it. A lot of physicists actually kind of regret the choice that got made. Wouldn't it be nice if electrons were positively charged and protons were negatively charged? There's a point of view there, but the convention is standard, it is settled, and you just have to go with the convention, arbitrary though it is. Here's the arbitrary convention. If you have a two-dimensional region, such as, for example, maybe this is part of a two-dimensional region, maybe this is part of a different two-dimensional region, whatever. Two-dimensional region. When we say the word boundary going forward, denoted, by the way, by this symbol here, that symbol means boundary. It's just notation. I know it looks just like the partial derivative symbol. Anyway, that's the notation. Boundary means oriented in a certain direction, characterized by the following feature. The following feature is that as you go in the correct direction, as you go along the boundary, the domain is on your left. That's the deal. Now notice, imagine that I'm standing here and I'm moving in the purple direction. If I'm moving in the purple direction, the region is on my left. If I'm standing here going in the purple direction, notice that the region is on my left. Everybody see what I'm talking about? If I were going the wrong way, the region would be on my right. So that's the convention. Okay. Like I say, it's arbitrary. There's nothing magic about the left. It's just the convention, just the choice. Now, there is a sloppy version of this that is not correct, and but it's correct in a lot of cases, and that just makes it dangerous because students get a little too comfortable with it, and then the other cases come up, and then they get wrong answers. The not correct version, the tempting but not correct version, is to say that you always go counterclockwise. Now notice, if you have a region like this, and you look at the boundary, and it's, well, look, there it is. That's that curve on the outside, and moving such that the region's on your left, it's always going to be counterclockwise. So it seems. Right? Except that not all boundaries are on the outside. If I were to look at this region here, this is a two-dimensional region, and if I were to talk about its boundary curve, well, along this part of the boundary curve, yes, moving such that the region is on my left does have me go counterclockwise. But along this piece of boundary curve, moving so that the region is on my left has me go clockwise. Anybody see the difference there? That's just the nature of geometry. It's too bad that it works out that way. But if you make your convention to be counterclockwise, and again, let me put a frowny face on this. This is not the right answer. Right? If you say always counterclockwise, then you're going to get some wrong answers. And in fact, furthermore, if you try to make a theorem that we're going to be developing into, right? If you try to make a theorem with this as your convention, the theorem will not work. It just doesn't work. So it's importantly not always counterclockwise. Okay, so enough about that, but make sure to be careful about that distinction. Okay, any questions about orientations on boundaries? Okay. All right, here's the next concept. Kind of seemingly unrelated. I want to talk, and this is an old idea we've talked about before. We hadn't used this word previously, but you're going to recognize the concept. The word I like to describe this concept with is accumulation. Certain kinds of questions have this feature of accumulation, and certain kinds of questions don't. So here's what it means to accumulate. It's the whole is the sum of the parts. It's every example that we've ever addressed with an integral, ever, is an accumulation. So in particular, if I talk about this whole region and ask, for example, how much mass is in that region? Well, the mass in that whole yellow region is equal to the mass in this purple region plus the mass in this green region. Of course it is. You can't just expect that just because you conceptually choose to sort of to subdivide a region into two pieces that all of a sudden there's going to be less mass or more mass. No, of course not. It's physical stuff. And so, of course, the whole of the sum of the parts, old concept, works for mass, works for population, works for, any kind of physical stuff, right? Okay. So, a little bit of grammar. I'll talk about mass then as being an accumulating quantity. This is a little phraseology. I like to talk about mass being something that accumulates over the region also. It's just lingo, but anyway, that's what we mean there. Is everybody comfortable with this idea of what I mean by accumulation? And I have a counterexample to follow up with in a second. Okay. So, here's the counterexample. Perimeter. Perimeter is not an accumulating quantity. And once I draw the picture, I think it's going to be perfectly obvious that it's not an accumulating quantity. Main reason I throw this out there is because I don't want us to make the mistake of thinking that every quantity of any sort that we ever encounter is automatically an accumulating quantity, because it's not. Right? It's a feature that works for some quantities and not for other quantities. So here's our first easy example. Perimeter, not an accumulating quantity. If I look at the whole and ask what the perimeter is, the perimeter is this orange distance. Right? Now let's look at the parts. If I were to look at this left side, its perimeter is this green distance. If I were to look at the right side, the perimeter is this blue distance. And now let's just kind of look at the picture. Is the green distance plus the blue distance equal to the orange distance? No, of course not. It's right there. A lot of the green and a lot of the blue is exactly the same as the orange, and then there's some green and blue left over. Clearly not the same. The whole is not the sum of the parts here. The whole is less than the sum of the part in that sense. So perimeter is not an accumulating quantity. Everybody see what I mean? Okay. Now there is something I want to point out. This is just a conceptual sort of way to think about what's going on here. That I'm thinking of perimeter not as being a feature of the boundary. I'm thinking of it as being a feature of the region. And that's going to seem a little weird, but I want the word perimeter to be something that you interpret as, if I give you an area, you come back with a distance. Area is the sort of the subject of what we're talking about when we say perimeter. The corresponding distance is the result. So don't think about the perimeter of the boundary. Think about the perimeter of the area. Okay. All right. Now, we've seen an accumulating quantity. We've seen a non-accumulating quantity. What's the difference? Why is one accumulating? Why is the other not? And it's tempting to say, oh, well, yeah, because mass is physical stuff. And ultimately, the laws of the universe, right? You just can't wave a magic wand and make mass appear or disappear. So the physical universe, reality of the physical world, you might be tempted to say, is what makes mass an accumulating quantity. There's a point of view there. Sure, that's fine. And it's tempting to say that perimeter is not an accumulating quantity because it's made up nonsense, that the physical universe it's just not physical. And if you're not talking about physical things, you can make up whatever kind of nonsense that you want to, and why would you expect them to behave like physical quantities? Again, point of view. It's not always that stark of a line, though. It turns out there is a mathematical construction that actually is an accumulating quantity. It's an accumulating quantity in this sense that physical stuff is, even though it's not physical stuff. And here's what it is. It's a vector line integral. Circulation. Right? And this is one of the really huge points of the theorem that we're in the process of developing. It's this thing called Green's theorem. We're going to get to it pretty soon. Hopefully before the end of today. I'm optimistic. And ultimately, deep down underneath it all is the fact that we're about to discuss that boundary circulation accumulates. Okay, now, I owe you an explanation for why does this accumulate. And let's recognize it kind of at a glance doesn't look like it should. After all, boundary circulation happens on perimeters. We just got through agreeing perimeters don't accumulate. So it seems like this would be kind of, I'm not going to say doomed, but we're betting against maybe in our initial intuition here. So, but let's walk through it slowly and carefully. Let's think it through. Starting with a hole. Let's look at this whole region here. What is the, how would I represent on this picture anyway, boundary circulation on this whole solid? Keep in mind what we're talking about, boundary circulation. And here we go. And I kind of regret my choice of yellow there. I'm going to switch to orange. Missed. Boundary circulation is an integral that happens on that boundary curve. I said the magic word. I said the word boundary. Boundary means oriented. I need to indicate which direction, what orientation is the circulation that we're talking about. We have rules for this. You have to follow the rules. The word boundary means such that the region's on your left. That means we're talking about circulation this way. So this is how I'm geometrically going to represent the boundary circulation on the whole. Now let's look at the parts. And this region on the left, what is the boundary circulation on this region on the left? Well, the boundary circulation is like this, and again, the orientation matters, so let's go ahead and put that in there. But wait, part of the boundary. of that green region on the left is this this kind of middle piece there, right? And again, we're anticipating that's the first glimpse of why this isn't going to work. It's that stuff in the middle, right? So anyway, slowly and carefully, there's our boundary circulation of the left piece. Now we look at the right piece. There's my right piece. Boundary circulation. Again, moving so that the region is on my left. Don't forget to close it off. Like that. Now, is the whole the sum of the parts? Tempting to say no. I see a lot more orange and blue than I see, I see a lot more green and blue than I see orange. Right? But now, let me delete the orange parts that clearly are the same as the green parts and the orange parts that are clearly the same as the blue parts. Right? We get rid of all of that. This is what's left. This is what we would have to claim is the difference between the whole and the sum of the parts. And it's tempting to say, yeah, look at that. There's a difference between the whole and the sum of the parts. But the problem is, there isn't really, because that is two line integrals on the same curve with exact opposite orientations, and that green piece and that blue piece cancel. They add up to 0. So amazingly, even though perimeter crashes and burns on the accumulation feature, boundary circulation doesn't. Boundary circulation, there's no difference between the whole and the sum of the parts. So boundary circulation accumulates. Everybody with me? And I claim this is ultimately what makes it all work. This is the kind of the nugget. This is the kernel. This is the cherry at the center of the candy that is Green's theorem that we're in the process of developing. Is this point right here? So make sure to give yourself time to digest and get comfortable with that. Okay, and then real quick observation. I divided the region up here into two pieces. Doesn't really matter. I could have divided into any number of pieces. Doesn't matter how many pieces I divided up into. Let's look over here at this scenario. Imagine if I were to look at, this region here. Well, boundary circulation is like this. And then I imagine I were to look at this piece here. Boundary circulation, boom, 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 etc., etc., etc. Do that on every one of these pieces, and notice you get massive cancellation in all of the same ways. On this edge, there's cancellation because we have two passes on the same edge with opposite orientation. They cancel. Likewise, on that edge, cancel. Cancel, 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 cancel. You see the pattern. Everything kind of, if you will, in the interior, it all cancels. The only things that don't cancel are these pieces that were kind of on the edge, if you will. That there is nothing on the other side of it to cancel with. And so you end up with just, stylus. Boundary circulation. Everybody see how that works? Divide into as many pieces as you want. Okay. All right. Now I want to remind y'all as we're developing these ideas, it's tempting to think of boundary circulation, such as this here, as a feature of the perimeter. Right? Because after all, that's where it's computed. This boundary circulation is it's computed on the perimeter. We think of it as a feature of the perimeter. Again, I remind you, let's not think of it that way. I think it's important to think of it as a feature of the region, the two-dimensional region of area that whose boundary we're looking at. So think of it as this region, this area, whose boundary perimeter is computed by by that. Okay. Now let me show you sort of why we care about this. I think it's important again to try to develop intuition and develop points of view that will allow for intuition to have all of its opportunities to flourish. So if I were to think of boundary circulation as happening literally on the boundaries, I could ask a question like this: how much of this boundary circulation is happening here? And it's tempting to say, that's a ridiculous question. The green curve is unrelated to the orange curve, and that doesn't make any sense. I don't even understand the question. How much of the orange circulation is happening on the green? No, they're just disconnected, right? But instead, better, let's think of it again in terms of the areas. If I were to ask how much of the boundary circulation on this orange region, how much of that orange region's boundary circulation is happening in this green region? Well, that's a reasonable question all of a sudden. That green region is a part of the orange region. And in the same way that I could ask how much of the mass in the orange region is happening in the green region, I could ask how much population in the orange region is happening in the green region. I can likewise ask the same question about any accumulating quantity. In particular, I can say how much of the boundary circulation on the orange region is happening in the green region. That's a perfectly reasonable question. It's an accumulating quantity. The whole is the sum of the parts. Notice the way I've written down the arithmetic here in this example, and this is arbitrary. I just made this up, but I think it's nice to have a sort of a picture. If I know that these line integrals are, that orange line integral is 6. I just made this up. And what did I say? Orange. This green line integral is 6. And if I were to say that this, let's say it works out that this orange line integral is 33. How much of that 33? How much of the orange line integral happens in the green region? Well, 6 of the 33 is happening in that green region. And it's a perfectly reasonable question because the green solid is literally part of the orange solid. Yeah.
But isn't all of the green one being canceled out by its boundaries?
Well, when you do the addition, yes, and that's why the whole is the sum of the parts, and that's why we have an accumulating quantity that makes the question a reasonable question to ask, right? Like with mass, right? But nevertheless, this colors. I got to be more careful about that. This green circulation isn't just 0, right? By itself, it's a thing. By itself, it is 6. And yes, you're absolutely right. When I add all of these other things to it, then all of that's gonna cancel. Those pieces are gonna cancel out, and only kind of these pieces are gonna remain. But that doesn't happen until I add in all of the other pieces. Yeah. Does that make sense?
Yeah.
Yeah. How we doing? So what I'm trying to develop in y'all's minds here is this idea right here, that even though it doesn't look like it, boundary circulation, you should think of it as being kind of like mass. Think of it as a stuff. Think of it as being physical. It isn't. But it behaves like it is. And if it behaves like it's physical, if it has its accumulation feature like it's physical, you can think of it as happening over the interior like it's physical. Then it's, for intuition purposes, awfully convenient to think of it as if it's physical. So anyway, that's a strong encouragement for how to think about boundary circulation. You should think of it as a stuff. You should think of it as a feature of the region, not the perimeter. And you should think of it as being physical stuff, kind of like mass. So, yeah. All right. How are we doing? Is everybody happy? I know it's weird. I told you it was weird, right? Fair warning. Okay. All right. So here's the thing about stuff. You can talk about densities. Right? Now, old concept, if you have a little piece of area and you ask, okay, well, there's a certain amount of mass in that area, and there's, of course, a certain amount of area that it's distributed over, just looking at that little rectangle right there. It's perfectly reasonable to talk about how much mass per unit area. And we have a word for this. We call it mass density. And I want to remind y'all that we've talked about various different kinds of density. We've talked about population density. It's not literally how dense is the population, right? It's quantity, namely how many people per unit area. In the same way that here we talk about quantity, namely mass per unit area. And again, we've done this in different ways, in different sort of physical applications. Think of density in general to mean any accumulating quantity, whatever accumulating quantity you happen to be talking about, per unit size. In this case, area, because it's area. So, accumulating quantity per unit size. Well, here's the thing. We have ourselves a brand new accumulating quantity, boundary circulation. It's an accumulating quantity. So in the same way that we talk about mass density, I want to talk about circulation density. And again, I know that's a trippy idea. We think of circulation as happening on the perimeter. Try to wean yourself off of that. Don't think of circulation as happening on the perimeter. Think of circulation as a feature of the area. And thought of as a feature of the area, you can talk about how much circulation there is. Let me get to the picture here. You can talk about the circulation for this area. Computed on the boundary, don't be too impressed by that. Circulation for that area divided by the area on whose boundary you're doing the circulation. And that circulation per unit area, again, it's accumulating quantity for an area divided by the area. That's a density. So this is what we mean going forward when we say circulation density. I mean circulation per unit area on whatever region you happen to be addressing. Everybody okay with that? Now, again, it's conceptually weird, and don't think of this lecture as the time that all of these ideas are going to comfortably digest in your heads, right? Spend some time outside of class letting all this kind of settle in. But this is what you want to sort of be thinking in terms of. Try to get used to the idea of circulation, again, as a physical stuff, as a property of the region that you associate it to. And as such, you can talk about its density. Okay, now, what can we say about this density? There's some formulas and notations. I am going to sweep the calculation under the rug. It's perfectly doable. It's in the book. It's perfectly accessible, and you can read it, but it takes a fair amount of time to compute this formula, and it's ultimately just a calculation. I think the intuition and the concepts here are much more challenging than the calculation itself, which even if you do read through it, you're just going to fairly quickly forget how that calculation works. So that part I'm happy to sweep under the rug, and here's the punchline. You can just take this as a given. Given a vector field, the circulation density, if you were to do this calculation here, like, set up a little region, look at the boundary, parameterize, blah, 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 take a limit as the area goes to 0, what you will find the circulation density to be is this formula right here. dq dx minus dp dy. Keep in mind the coordinates of the vector field are p and q. That's the formula. It's not magic. It's just it's a calculation. This is the end of it, and let's just take that as given. Everybody all right with that? Okay. All right. So there's different names for this, different notations. This is the operator that we're going to find as the integrand of the theorem we're about to write down that we're going to get to momentarily. This is the operator in Green's theorem. And so I think it's very reasonable to call it Green's operator. I don't know. I like that. I find that's natural. Okay? So you're going to hear me calling this Green's operator. It is sometimes called curl. This makes me a little bit uncomfortable. We've talked about curl previously. And when we talked about curl, we talked about it as being a vector. Right? You look back at back to chapter 3, you look at the formula for curl, vector. This is not a vector. Now, it turns out that yes, there is another theorem that we're going to encounter in 3 dimensions. We're not in 3 dimensions right here. We're in 2 dimensions. Very importantly, 2 dimensions only. But yes, there is another theorem that we're going to encounter in 3 dimensions that has a lot of the same earmarks as what we're developing here. You're going to notice that when we get to it. And yes, the operator that comes up in that 3-dimensional theorem, it is called curl. And therefore, this is analogous to curl. I just think it's a little bit of a stretch, a little bit of an overreach to therefore call this the same name and to call it curl. Curl, as we're going to know it, is a vector. This is a scalar. To me, that's different enough that I think it should have a different name. Nevertheless, be aware, some people are going to call this curl. You should know what they're talking about if they say so. So heads up for that. It's also commonly called rot of F. Rot for rotation. After all, we are talking about a circulation. Circulation, we've literally talked about as something that recognizes how the little leaf on the surface of the river starts to rotate because of the flow of the fluid. Right? So rot as an abbreviation of rotation, kind of a reasonable choice. I like this one, rot. I like this notation here that I think I may have made up. It's also possible I may be copying from someone else that showed me so long ago I don't even remember. Very possible. But this use of the GRN is just kind of an abbreviation of green, which again I've already said I think the most natural thing to call this is Green's operator. So GRN seems reasonable to me. Anyway, it's not as common as of a notation. Lastly, there's this formula right here. This one rubs me the wrong way. Oh man, look at this. The thing here, F, has 2 coordinates. And then they're talking about, in the notation, they're talking about doing a cross product with it. There is no cross product for a vector with 2 coordinates. Now, I know why the notation I know where this comes from. This is kind of sort of that's the formula for curl, so you can kind of sort of see how they, it might be motivated. But this just rubs me too wrong, and I don't like this notation. You're going to see it's in the book. It's on our textbook. So I can't tell you you can't use it, but I can tell you I really don't like it. And I encourage you to distance yourself from this one. Okay. All right. Now, all of this said, let's put it all together. Here's the big theorem. This is Green's theorem. We've already proved it. We just haven't connected the dots yet. So here's the connections. We've agreed that circulation is a kind of a stuff. It's kind of like mass. It's a physical-ish, it's not, but we can think of it as a physical-ish stuff. And so I'm going to give it a notation. In fact, we have a pre-existing notation for circulation. Sigma, right? Sigma for circulation. So there's that as a concept, thought of as a quantity. We've talked about the fact that it accumulates. The whole is the sum of the parts. That's all accumulation means. That's all this double integral notation means, is chop it up, add it up. Again, already established. And then there's just the little matter of, I have to zoom out, of recognizing that, a little bit more, that we have this concept of a density. That circulation per unit area is what you multiply by area to get circulation. right? And that the corresponding density, think of it however you like. I've written it here using that notation, but feel free to use any of these other, I guess it'd be weird to put words in there, but any of these other things would be reasonable to put in there. Again, I don't like that one. But a bunch of different notational alternatives for what you put in there as your density, as your circulation density, which therefore ends up, you'll notice, being your integrand in your integral. And this is Green's theorem. Green's theorem says that boundary circulation is a double integral over the interior of Green's operator. And there you go. So, Green's theorem. Okay, we got to stop for today. This is a good stopping point. We will pick up next time with some examples. Thanks for coming. See you on Friday.